Hello everyone. I wanted to continue our discussion about Yoda, and today I wanted to discuss how to deal with rationality. So most of the prior work in security of blockchains has looked at threat model which has honest nodes and Byzantine nodes. And of course, these models have been used traditionally also, and maybe they make sense in some situations. For example, you have, let's say, a group of banks, let's say, which are running a distributed system. There's a distributed system here, and a few of them get compromised. So these, let's say, these two get compromised. So it makes sense that the nodes which are not compromised are running the algorithms they were supposed to run, right? And except for the ones which have been compromised and they become Byzantine. Okay, so these models do make some sense, but in a permissionless setting, like we have miners in Bitcoin and so on, we have to think a little bit differently. So maybe what is more realistic is that you have rational nodes which try to maximize their reward, and there could be a small set of Byzantine nodes. So these nodes don't mind losing all their money, so they don't care about losses. So they arbitrarily deviate from the protocol. Okay. So this is more realistic in practice, and you might want to think what would be a good model for Bitcoin miners. So how does everything work out correctly? I mean, if people are trying to maximize their reward, then why should they be following Bitcoin's protocol? And of course, Satoshi was very clever, and I think he understood this whole notion of rationality. So he knew that people in the real world want to make money, right? And if you can incentivize them to behave honestly, that is behaving honestly is the rational thing to do, then they will behave honestly, right? So he offered this thing called a block reward, and we can do some back of the envelope game theory to figure out that actually a good strategy for somebody is to be rational, to follow all the Bitcoin rules. Anyway, so I wanted to consider something like a rational plus Byzantine model for Yoda. So this is, let's say, this is model 1, which we considered till now, and model 2 would have rational plus Byzantine nodes. Okay. So it turns out that actually dealing with a rational miner is very tricky, because what would somebody do if all he cared about is maximizing his rewards, and the attack space is too wide? We could think of something like a bribe attack. So what would be a bribe attack? So you bribe somebody, let's say a rational miner, some amount to deviate from the protocol. Okay, so offer a bribe to rational miner to deviate arbitrarily. Okay. So this is a very difficult attack to handle because you can always offer a large enough bribe for a rational miner to do something. So even if you say that a rational miner has to deposit some money, or all people have to deposit money on the blockchain, let's say the people who are involved in Yoda, for example, right? They in the miracle algorithms, people in the stake pool, let's say, are depositing some money. But suppose you offer a bribe which is larger than their deposit, they don't mind losing their deposit in that case, and they would behave arbitrarily, right? So if the bribe is large enough, you can make a rational miner pretty much do anything. Okay. Rational is a very difficult model to deal with and show that it will always work, because there are things like bribe attacks which can always break the whole system. So what we do in our paper, in the Yoda paper, is that we consider, instead of rational, we consider nodes to be quasi-honest. So this is better than saying they are just purely honest and no incentives will get them to do anything. So we allow a few attacks, and of course we show how to handle them. So let's think about how miracle works. So let's say we have S1 and S2, and this is in the first round. Okay, this is the number of nodes which have submitted solution S1 and S2 and so on. Okay. And let's say that a couple of rounds have progressed. So suppose these were the votes, and normally, I mean, you can just count the number of votes because these are all there on the blockchain. So in round 3 we have a particular execution set which is chosen, and now we are going away from the honest Byzantine model. We are saying, suppose the nodes are they are somewhat rational, they want to make money, okay, and they want to maximize their earnings. So suppose you have a lazy person who's selected in the execution set, okay. So this computationally intensive transaction requires some effort. He has to use his CPU to perform the computation, and assuming that everything goes off well, he gets a reward. Okay. So suppose so what does a particular miner gain? Well, he gets some reward for doing the computation. and at the same time there is some loss that he has to incur. And this loss is due to computation. Okay, so he loses a little bit of money in doing the computation. Okay, but the whole thing has to be designed so that the gain is larger than the loss, so that somebody actually does the computation. Okay, so this is like the transaction fee, which is distributed among all the people in the execution set. Okay, so suppose we are in round 3 now, and you have a lazy miner. Okay, so lazy miner wants the gain, but he does not want the loss. So can I get the reward without performing the computation? Suppose a miner is thinking along the, not miner, suppose a person in the execution set is thinking of along those lines. Okay, so what would he do? And suppose you were one of these persons in the execution set, how would you do it? You have seen most of the votes in round 1 and round 2 have come for S1. So you might say, I am willing to guess. Okay, so you guess S1 is the solution, and you don't do the computation. So you just submit S1. Let's say there is some ES3, there are several nodes. So one of these nodes might get lazy and submit it. Okay, so there is a chance that maybe the solution is S2. That might happen, but that's less likely than S1 being the solution. Okay. So Miracle is itself not sure, which is why it has asked for a third round. But this miner might say, I don't want to know things so sure. I don't mind. Let's say the chances of S2 being the solution is only 1 in 100. 99% it's going to be this, so I will vote for S1. And of course he would have to calculate what are the chances of his winning and so on, because there's a chance that if he's guessing he might also get it wrong, right? But what might happen is that a lot of votes here, if a lot of people are rational, they might all vote for S1, and this is a problem, that they have voted for S1 without doing the computation. So this is a serious problem, because Miracle assumes that nodes are at least there are this set of honest nodes which are doing the computation correctly. Okay, so it's designed in that fashion, and things can go wrong if there's pretty much nobody doing the computation honestly from a particular round on. So the Byzantine nodes will submit whatever they want, but if the quasi-honest nodes are going to do this, they tend to be lazy, then we are in trouble. Okay? So it is possible if lazy nodes don't compute, then no one does the computation. And so Miracle's assumption will break down. So in our quasi-honest setting, we allow the nodes to try to do this attack, and this is called a freeloading attack. So what is this attack? Well, a quasi-honest nodes see votes in previous rounds. Okay, and so they may skip computation. If they can guess the solution, provided they make more money that way. Okay, so essentially what they want is that the expected winning is higher if you get if the quasi-honest node guesses rather than doing the computation. So in the paper we do a game theoretic analysis for this. Right, game theory can be a very tricky subject to deal with. We are probably seeing it in play in politics all the time, right? Geopolitical situations and so on, right? But because each party sort of is trying to guess what the other is going to do. So I think you may know that one of the founders of game theory was von Neumann, a very famous computer scientist and mathematician, and essentially von Neumann was recruited by the US government to give him advice during the Cold War about what they should do for their military policy and so on. Okay. Anyway, so we have to do an analysis to figure out how to do this. So what we will do is we will we will change the system a little bit from what we discussed in earlier classes to ensure that this second option of doing the computation is better. So guessing is let's say one option, and doing the computation is what we would ideally want. So we design a system so that option 2 is better than option 1. Okay. So just like Satoshi says that solving the proof of work puzzle is better than not solving the proof of work puzzle, right? Somebody might create a fake block and send it out, but that's going to hurt him because nobody is going to include that in the blockchain, right? But if you do the proof of work correctly, you earn a lot of money. So Satoshi ensures that doing things honestly is a better option for anybody. Okay? So let's see. what we are going to do, right? So another attack which we allow is something called a collusion attack. So what is this collusion attack? So here in the previous freeloading attack that we talked about, each particular node in the execution set was making a decision on its own. It was saying what were the votes submitted earlier rounds and then what should I submit, right? But now we are saying in the collusion attack, the nodes within the execution set might collude with each other and decide what to submit. So they might sort of say that okay, S1 was submitted mostly here, and if all of us together submit S1 in this particular round, then we know how miracle is going to work, right? It has all those summation formulas and so on, that we are going to cross the threshold if all of us together submit S1. So let's do it, irrespective of whether it's right or wrong, right? So they might collude, and we allow this too in our paper, and we design a scheme to reduce the chances that this would succeed. Okay. So in collusion attack, so if so we allow let's say can collaborate to submit a solution provided its expected profit, I should say winnings like we did previously, the expected winnings, but maybe we should use profit rather than winning. So that expected profit is more than if they did the computation correctly. Okay, so the idea here is that they might get together and say, okay, S1 was submitted in the previous two rounds in majority, and we know that if we get together and submit S1 again, then we are going to win. We are going to win the game, right? Miracle is going to decide in terms of S1, and in which case we get whatever reward, right? The transaction fee gets divided. Okay. So again, in the paper we show how to deal with this. The question is there an easy way to do this? I mean, how do we deal with this situation? It seems very tricky. We didn't have to deal with this at all when we handled honest and Byzantine nodes. The Byzantine nodes could do whatever they want, and the honest nodes behave perfectly normal. Right? So now how are we going to deal with this, right? And you might think about collusion. How to prevent collusion? Well, the thing is, if different ES nodes can identify each other, then they could probably do a collude together, right? So what we might want to do to prevent collusion is to ensure that no ES node should let another node know that it is part of the stake. Okay. We should sort of punish nodes if they reveal that they are in the execution set too early, right? That may be one way to do it. Also, of course, there is some computational effort, so communication effort has to be put in for different ES nodes to talk to each other in this particular collusion attack. And if that is more costly than actually doing the computation, then it doesn't make sense to do that. You might as well do the computation. Okay, so we'd have to think about something along those lines to deal with collusion, that each node should not reveal that it's part of an ES too early. Okay. What about freeloading attack? So let's look at this figure. So suppose we are in round 3 and S1 has been submitted in each of these, right, in majority. So how would we prevent a freeloading attack? How do we force somebody to actually do the computation? So this seems very tricky, right? So one idea is that suppose we don't actually submit S1, suppose we submit something different in every round. Maybe there is some randomness over here, and suppose we submit, we have that people in different rounds are forced to submit something different. Okay. The question is whether that would work or not, and that turns out to be tricky, and let's think about it. So dealing with freeloading, so these are just ideas. We'll see what we do later on in the paper, and of course maybe you will come up with a better solution than what we did in the paper, right? Just because we published something doesn't mean that is the best solution possible, right? So suppose instead of S1, S2, suppose I have something like here S1 1, and let's say that, let's say S1 dash, right, and S2 dash, and in the next round we changed it so that you had S1 double dash and then S2 double dash. Okay, and so I'm saying if everybody, let's say that this is the correct solution, if honest people did the computation in the next round, they would end up submitting S1 double dash, right? And in the third round I would have S1 triple dash and so on, right? Maybe S2 triple dash. So these are all Byzantine solutions. Suppose we were able to do this, right? We add some randomness to the solution. Okay. So, for example, suppose earlier we said that S has to be hash of the state. So this is what we had earlier. Hash of the state, let's say at the end of the computation. Okay, and so if we wanted to do something like this, what would we have? Well, we could have hash of the state concatenated with the round number, something like that. Okay, then you would have something like this. And so you would not be able to, just by looking at this, figure out what is this going to be, right? Because here you have hash of state concatenated with 1, here you have to have hash of the state concatenated with 2. Okay. But what might happen is that somebody here might get information about this state, right? So let's write that down. So member of ES3 may get the state from some member of ES2 or ES1, and then he can compute whatever S1 triple dash, right? So suppose he gets the state from somebody who has submitted this, he can just verify that it is indeed the state by concatenating 1 to that state. Okay, and he can also see that, okay, if I concatenate 2 to that state and take the hash, then I get S1 double dash. Okay, so then he doesn't do the computation, and then he can just submit S1 triple dash. And he computes right. So this is one issue which comes up. A second issue which comes up is with the miners. So remember that miners need to compute summation of C1k square minus whatever, right? I not equal to k ci j, sorry, this was j. So miners had to compute this, we said, to get the log likelihood ratio. Okay. So how are they going to do this if we have the scheme that is shown up over here? Because, okay, I can get the counts for this one and for this one, but the problem is I need to know the counts for the same solution in the next round. So if I can't do a mapping from S1 dash to S1 double dash and so on, then how am I going to get these numbers to do this summation? Right? Because the miners are just seeing these, they don't have the state and so on, they're just seeing the hash of the states being uploaded and counting the votes corresponding to those hashes. Okay? So this is a problem with these are problems with the scheme that I've just described. So what we do in Yoda is a little bit different. So we have two components for what is submitted. So we submit the regular state, let's say S1 and so on, and we have to add a pseudo-random component. I'll just call this S, and R changes from one round to the next. Okay, so you have to submit two numbers, S and R. So all honest miners will have the same S in every round, but for honest miners, R will change from one round to the next. But that's okay. So the R's will change something like this, like what I said, it keeps changing from one round to the next, but the component corresponding to just the state of the system at the end of the computation, that should not change for honest miners from one round to the next. So that is going to help the miners. The miners are going to use this S component to actually count the votes. So let's just say that the miners, so the R component changes from one round to the next, and this makes it hard for them to do freeloading. So I can look at the previous rounds and I can guess what S is going to be in this round, but I don't know what R is. Okay, and R, we are going to force the person to do, the people in the execution sets to do most of the computation so that they can get R. If they don't do most of the computation, then it's going to be very hard for them to calculate what R should be in that particular round. Okay. So to summarize what we want to do, in round 1, suppose we have S1, let's say S2. We would also want to have an R1 and R2. And in round 2, let's say the number of votes change for S1 and S2. So these S1 would not change, at least the correct solution would not change. Of course, the Byzantine adversary might change his solution from one round to the other, but just for convenience, we are keeping it the same. But this R1 is not going to stay the same. Okay. So we will have something else. Let's say all the honest miners, this time in round 2, they are going to compute something else. Okay, and so we are going to let's call this R12 and let's call this R11, and maybe this gets mapped somewhere else. Okay, so this remains the same, and this would be changing. So this is going to help the miners count the number of votes for different solutions. That's not going to be a problem. This is going to change from round to round, so it's going to be hard for the freeloading attack, because just by looking at what was submitted in the previous round, you are not going to be able to figure out what this is going to be, right? So if a miner is, let's say if a ES node is lazy, okay, it's quasi-honest, suppose he copies this S1, let's say over here, and suppose he just copies R11 again over here, okay, so his vote would be counted towards S1, that would be done, but when it comes to rewarding him, he would actually get punished, because let's say all the honest miners will actually compute this R12 and submit it, and let's say that eventually we decide that this is the correct R12, but if somebody submits R11, he would get punished later on by the miners. Okay? So in order to get this R component, the ES nodes are going to be forced to do most of the computation of the CIT, and we'll see what I mean exactly by that. So let's see how we are going to do it. So the second major algorithm of our paper is called Rice, and it stands for randomness inserted contract execution. So first I'm not giving you the actual Rice algorithm, but let's make an effort. So what I have here is an execution trace, which we've seen earlier. So we start from the initial position, and let's say we end at T, instruction T. So what are we going to do? So we want to produce this R, and we want to ensure that whoever is trying to submit a solution is forced to do this computation in case he wants to generate R. Okay. And of course you might come up with an algorithm better than Rice, and you can of course maybe propose it, but here's what we're going to try to do. So suppose I generate, let's say, a random number. Suppose over here I initialize R to be, let's say, some random, pseudo-random number, which is dependent on the round number. Okay. So for example, let's say that this is hash of some, let's say, some seed information. I'll just call it R init. Okay, or let's just call it a seed. So maybe in the paper I use a slightly different notation, but suppose I do this. Okay, so let's say the seed is dependent on this, it's decided by various factors. Let's say uses some hash of let's say the block containing the CIT, etc. Okay, so this seed remains the same for every CIT. I mean, we could do something different also, but everybody knows what this seed is supposed to be, and you concatenate J to it, and you take the hash. So this initial value of R here when you begin changes from round to round. Okay. Now what I'm going to do is I'm going to choose a particular position here. Some position Pj, one, let's say this is the first attempt, and we'll see finally what Rice does. So what we are going to do is we are going to take the state at this position, okay, and what we are going to do is that we are going to update R is equal to, let's say we do this, the hash of the earlier value of R concatenated with the state of the smart contract, okay, at this particular position Pj. So this position changes randomly from from one round to the next. Okay. So suppose this is how we generate R, okay, and so clearly since this Pj is changing from one round J to the next, the value of J is going to be different. So suppose this is the final, this is what is the final value of R, which is submitted by the ES node. Okay. So yes, so we've achieved something that we intended to, that you get a different value R in every round. But what could be some of the shortcomings? Okay, so we said let this Pj, let's say it is uniformly.
Sorry, I'm happy.
It's chosen uniformly from 0 to T. And the question is, what might go wrong over here? So one question is, how to know T? Okay, so there has to be some deterministic mechanism, right? I mean, and I'm just eyeballing it and saying, okay, suppose I know that it's going to take T steps in order to execute this smart contract, and then I choose randomly between these two, right? But the question is, how do you know what T is? I mean, and the miners themselves have not executed the whole smart contract, so they may not even know what T is, right? And so the system has to figure out some way to do that. Okay? That's one question. Another problem that comes up is, okay, suppose an ES node has to calculate this R, and assume that it's lazy, So what is it going to do? It is going to compute from 0 to pj, right? It gets the state at pj and then it skips this much. It skips the computation from here onwards. Because after all, the value of r is determined at this position pj, and so that's the end. I mean, maybe pj was somewhere over here and this ES node would be able to skip the computation all the way after that, right? So that is another problem. So we want the ES to do the whole computation if possible, right? And ES node, which is quasi-honest, I mean it's lazy, can skip computation after PG. And this is something we don't want. We want it to do the full computation. Okay, so you might say, is there a fix for this second problem? Suppose we ask it to, suppose we force it to actually update the state at this last position t. Okay, so that seemingly solves the problem that he would have to do the computation all the way up to here. But the problem is that maybe he can get this state from somebody who has done the computation in the previous round, the final state, right? So it's a tricky situation and we'd have to look at it properly using an appropriate threat model. And the reason is that somebody who has submitted an R value in the previous round, suppose that final R value was dependent on the state over here, he might be able to actually prove to the ES node in this round what was the state over here. Okay, so he might say that, okay, see, this is what I have submitted, and indeed you can verify that this was my state over there. Okay, he might be able to do something like that. Okay. So what we want to do is we want to choose let's say some points, maybe more than one, at which this state is going to be updated. So let's look at a second attempt. Suppose every n execution steps we update. Okay. So what would be the issue over here? Well, so let's say this last amount he could skip over here, and this is of length order of n, right? N steps. So every n steps we are forcing it to update. Okay? So here the issue is that the number of update steps. So the update is the same over here. We are always doing r is equal to hash of r and the state at this position. Right? And of course here we would do it at we put state 2n and so on. Right? The number of update positions is going to be order of t by n. Okay, so n is something fixed, so it's going to be order of t again. So this solves the first problem to some extent. How do you know what t is? So you don't need to know t, you just say that n is, let's say every 50 steps, let's say you're going to update this r value. Right, so t can be anything. I mean, it can be 1 million, 2 million, or whatever, but you would have order of t updates, which is not good. Earlier we had order of 1 updates, right? So that was the good thing, but then we had these issues. Okay, and so here the good part is that the amount skipped is small. Okay, so in the first attempt, the number of updates was what? Order of 1, right? One update, and the number of steps which could be skipped at the end is how much? It could be potentially order of t, right? So here we've changed it. The amount skipped is order of n, small. It's a constant, and here it is order of t. Okay, so we should compare these. So this is not very good. So of course we were wondering what to do. What should we put into the Rice algorithm? So the third thing is that you increase exponentially. So n is again some constant, and what we are going to do is we are going to update the value r at these different steps. Okay, and we're going to increase them, space them out exponentially. So the number of updates is going to be small. And again, we don't need to know this t in advance, right? But the amount that could be skipped could be large. So in this particular figure that I've drawn, it's small, but typically the last amount, this last step which could be skipped, is roughly the size of this particular interval. Okay, and that too could be very large. So we may skip half of the computation at the end. Just because we are doubling this gap, you may actually end up with almost skipping half of the computation. It's possible. So we can maybe draw another diagram here. So suppose it looked like this. So 16n could be way beyond t. So the ES node stopped updating r at 8n. Yeah. So we might skip half of the computation at the end. So amount we skip is again order of t. Right. So what we do in the Rice algorithm is the following. So suppose I set a particular array to have these values. So what we're trying to do here, and I'll show you exactly how we do it in a moment, but what we're trying to do is we are not going to double every time. We want to increase this interval, but not so drastically. We don't want to double it. So it's like a sub-exponential increase. And I'm going to use this array to do that. So what I put in this array is that I have the numbers 1, 2, 3 and so on, and each is repeated the same number of times as that number. So 2 is repeated twice, 3 is repeated thrice and so on. Right? So how are we going to do this? So initially we start our execution at position 0 and I set small k is equal to the 0th location, which is equal to 1 over here, right? And I'll show you how we are going to jump over here. So what we are going to do is we skip. So we skip over by 2 to the power of k plus random 0 2 to the power of k to find the next update point. So I've used the skip in a different sense over here. So earlier when I said that the lazy ES node is going to skip computation at the end, I mean he just doesn't do the computation. So here of course he keeps doing the computation, but I'm just saying when is the next location where he has to update the state. You don't want him to update this R value at, I beg your pardon, we don't want him to update, I should say for R. So you don't want R to be updated at each and every execution step, because that's an overkill. There would be too many points at which you want to update R at, right? So that's the point. So let's say that we have to use this formula. So there's a way to get this random thing. It's of course pseudo random. So we use some pseudo random method. So we are skipping by a certain amount to find the next update point. So this particular ES node is going to do the computation at every execution step, but it's going to update R here. Right? Now again he does the computation, but we use this formula. So here we are going to set k is equal to k of 1. Okay, so its small k value has increased to 2. So we jump by a particular amount given by this, right? So we are at least jumping by 2 to the power of k plus some random number, right? And this is of course going to depend on the round. Right? So you want different points to update points to be chosen from one round to the next, right? And maybe this time we jump by a different amount, right? So this is where we update R, right? And these are changing from one round to the next. Okay? And this you can show that this is a sub-exponential increase. So because we are not doubling every time, we are for example, whenever it is 3, roughly the jumps are going to be the same. It's not doubling here. Right? And what we show in the paper is that the number of update points for R is it's a square of log t, so that's not terribly large, and this last jump, which we said you can skip. So this is the last update point. So this allows a lazy node to actually skip this computation. Right? So what is this going to be? So this is going to be of the order of t divided by log t. So not as bad as order of log t. Okay, something lower than that. And of course, you might be able to find a different way of when to find these update points, right? So what we are assuming over here is that the final state, whatever is there at t, can be easily obtained by any quasi-honest node, any ES node, by contacting somebody who has done the computation in the earlier rounds. Okay, because in the ES nodes of the earlier rounds have submitted their values of R, right? And if we include this point in the computation of R, then it's very easy to find out from earlier round miners what exactly was the value of the state at this point. Okay, so those details are given in the paper. You can have a look at it. Right, so these are the two main algorithms, Miracle and Rice, which we proposed in our Yoda paper. Okay. So what I want to do next is to talk a little bit about game theory. So it may be something new to you, or it may be something which has been considered in another course. Okay, but it's something that we should consider in blockchains, because after all, the whole system of Bitcoin does revolve around game theory in some way. Okay, because why do these rational miners all around the world, why do they actually follow all the rules? Okay, so we'll do a little bit of game theory. We'll sort of brush up if it's something that you've seen before, or it may be something totally new. We'll go a little bit over it, and we'll study the freeloading attack and see under what conditions can we prove rigorously that our scheme is going to work.